Okay, let us continue with this integral. Integral psi star psi dx is equal to 1 by h cut integral from minus infinity to plus infinity phi star p comma t dp integral phi of p prime comma t dp prime into 1 by 2 pi integral minus infinity to plus infinity exponential of I by h cut p prime minus p into x dx. So, now I am going to evaluate this term using the definition of Dirac delta function. So, this can be written as h cut into delta Dirac delta function of p prime minus p. Okay, let us substitute the value here. The result is substituted in the integral, and now we are going to evaluate this one. This integral is shown here. This is also okay. Let us cancel one h cut from the equation. So, this is also evaluated using one of the properties of Dirac delta function. So, based on this property, the result will be because the integration is over dp prime, and the result will be consisting of this variable p, the other variable. Integral is over dp prime, so the result will be consisting of variable p substituted in the given function. So, we have the result phi of p comma t. Okay. So, I have substituted the value of this integral as well. Now, integral minus infinity to plus infinity phi star phi dp. What is this phi star phi dp? This is actually like in position space we have psi star of x psi dx. Okay, integral psi star of psi star of x psi of x dx is mod integral mod okay psi square dx. This is the probability density in the position space. Likewise, in momentum space, we can write the similar relation integral phi of p star phi dp, that is integral mod phi square dp. Okay. So, this is also a probability density in the momentum space. Like we define probability density in position space, we have probability density in momentum space, that is integral phi star phi dp, that is mod integral mod phi square dp. So, we can define the probability density in momentum space. Okay, now let us calculate the expectation value of operator for position coordinate in momentum space. We have already calculated expectation value of x in position space. Now, we are going to calculate the same expectation value in momentum space. So, let us begin with our definition of expectation value. Integral psi star x comma t. We begin with the expectation value in position space itself, and we apply the value of wave function using the Fourier analysis. And we are also not sure about what is the value to be given for a position coordinate, corresponding operator of position coordinate in momentum space. So, we are going to use our analogy we have a operator, momentum operator in position space is minus I h cut dou by dou x. Okay. So similarly, identical to that, we consider operator x in momentum space as minus I h cut dou by dou p. Okay. So we are going to use that operator for x in our equation. So we already know that psi star x comma t is this one, dp, then x, then psi of x comma t. I am going to give the value of x as this one, minus I h dou by dou p prime. Okay. Now we will consider this integral and we integrate it once. This is, the limit is actually from minus infinity to plus infinity. Okay, I'll take minus I h cut outside. So we have a first function into integral of the second. Because we have dou by dou p prime of exponential, we can directly write integral of the second as exponential, because this integral and the differential gets cancelled. So we have first function into integral of the second as exponential. Then apply the limit. Limit is actually from minus infinity to plus infinity. Minus of integral of derivative of first. We have a dou phi by dou p prime. Then again integral of the second. Exponential I p prime x by h cut dp prime. So we were calculating expectation value of x, position operator, in momentum space, and we have started with integral psi star psi dx, and for psi of x comma t we have substituted the value in using Fourier analysis, that is including the wave functions in momentum space. So we have this equation now. Now we have this equation. Now I am going to integrate the last integral, integration by parts. So first function into integral of the second. So actually we have dou by dou p prime. Okay. This is dp prime. Okay, so dou by dou p prime integral of dou by dou p prime of a function dp prime. That means integral and differential get cancelled, and first function into integral of the second means what we have is only exponential. So we can apply limits here. Then minus of integral of derivative of the first function dou phi by dou p prime into integral of the second, again exponential remains, dp prime. Okay. So this one, now when we apply limits, we are familiar with the properties of a wave function. Wave function is always supposed to be finite and single valued. That implies, as the variable, here we have variable p, so p tends to plus or minus infinity, phi should tend to 0. So considering that condition, we have, when we apply limits here, we will have a 0 here. Okay, so first term is 0. Now we have only the second term, that is minus of integral of derivative of first into integral of the second. Now substitute the result in the equation, this one, this is the result of the integration. Now what we are going to do is, we will integrate this one, integral over dx. For that all the functions including x is taken and combined. So it is 1 by h cut into 1 by 2 pi integral e raised to I p prime minus p into x by h cut dx. We have already integrated a similar function, so we know that it gives Dirac delta function, or we have actually 1 by h cut is there, and the result of this is h cut. So h cut get cancelled, and we have Dirac delta function delta of p prime minus p. Now again this is integrated, minus infinity to plus infinity, dou phi by dou p prime into delta p prime minus p into dp prime. Actually these two integrals are the same like we have used to find the probability in momentum space. So those two integrals are getting repeated here, this integral and this one. Here the only difference is we have, instead of phi, we have dou phi by dou p prime. The function is different here. So after this integration we will have the function with the variable p substituted in it. So this is dou phi of p comma t by dou p into dp. Okay. Now we take the I h cut, the constant inside. Here we already had a minus here, and it got cancelled here with the one of the minus outside, so you need not worry about the minus. Now the only constant we have is the I h cut. So we will take I h cut inside. We can write it integral from minus infinity to plus infinity phi star p comma t I h cut dou by dou p phi of p comma t into dp. What does it mean? This is the expectation value of this operator. If we sandwich an operator between wave function, complex conjugate of wave function and wave function, this means the expectation value of an operator. So here we have operator I h cut dou by dou p. So we identify it as the position operator in momentum space. So position operator in momentum space is represented as I h cut del p. Like momentum operator in position space, minus I h cut del x, that is the position, momentum operator in position space, and in momentum space we have position operator expressed in a similar way, that is I h cut del p or I h cut dou by dou p. So we can identify it as the operator x. So that is the expectation value of a position operator in the momentum space.